Welcome. Thank you all for being here. So I'm based at the VU University in Amsterdam. There are two universities there, and this is also called the Free University, but I think they're still debating about the English name. I'm going to take you to the aquatic world today, talking about fluxes of carbon in inland and coastal waters. Most of the pictures are taken by Chris Linder. He's great in the field with photos. He puts on his wetsuit and also, films us from the water in boats. So you're all familiar with this map, I suppose. My first slide, I thought to combine a little bit of numbers on permafrost, on water, and on carbon. So permafrost stores a lot of carbon, about 1,300 petagrams. And most of this is located in the Arctic Ocean watershed, which is here outlined in red. And that's about 20 million square kilometers. 60% of this is located in Russia and about 30 in Canada. 45% of this watershed is continuous permafrost. 13 is discontinuous and 18 sporadic and isolated. And the amount of water that covers this watershed, it's quite a lot, but it's hard to put a figure on it. About 16% of the land surface is covered by water bodies of 0.1 square kilometers and bigger, which is actually quite big if you think about it. So there's also much more water actually present as smaller streams and rivers and wetlands and ponds that are not included in that 16%. So it will probably be much more freshwater at most of these regions. All the Arctic rivers combined in this watershed drain 3,700 cubic kilometers to the ocean every year. That's about 10% of global discharge, but it's discharged into an ocean volume that's only 1% of global ocean volume. So the rivers have a very big impact in this ocean, relatively speaking. And then the coastlines of this Arctic Ocean watershed consist mostly of permafrost, and these coastlines there are about 34% of all the coastlines in the world. So I think there's a lot said this week about the permafrost carbon feedback, so I'm not going to talk about that much. But just briefly, this is normally presented as a vertical pathway. So you have, is this actually working? Right, yeah. So a vertical release by decomposition of organic matter of greenhouse gases, which are added to the atmosphere and lead to increased warming. But today I'm going to talk about the horizontal or lateral pathway. So all the organic matter that is released into aquatic systems after permafrost thaws. This pathway is basically not included in any of the climate feedback calculations. And once it is being released, it can either be decomposed, still continuously all along the whole aquatic pathway to the ocean, but it can also be buried in sediments, lake sediments, shelf sediments, and many locations. So I'll go through a couple of topics today, and the first one is organic carbon fluxes from rivers and coastal erosion. I hope you all had coffee, because I'm going to make a small comparison just to explain to you how we classify organic carbon measurements. We usually filter the water, and then we quantify what's on the filter and what goes through the filter. So you have a particulate and a dissolved fraction, and I think most focus is on the dissolved fraction. But the particulate fraction at certain locations and at certain types of thaw, it can be very high. So for pan-Arctic rivers, these estimates are pretty well constrained. The amount of particulate carbon is about 5.8 teragrams per year being released at the river mouth into the Arctic Ocean. DOC, so dissolved organic carbon, is much more, about 34 teragrams. For coastal erosion, this distinction is typically not made because it's calculated from the amount of sediments, usually, and then the organic carbon content. So this is released as both as PUC and DOC. And it also varies more because, well, it's harder to measure the whole coastline than the river mouths for a few big rivers. So if you add these up, you could get to a total organic carbon flux at the river mouth of about 50 teragrams. But this is, of course, at the river mouth, so at the interface between land and ocean. And that's totally not the whole picture. On the one hand, as soon as this organic matter is released on the shelf, things don't end. It continues to degrade. And examples of decay rate constants in the East Siberian Sea and Laptev Sea are 0.3 per year for dissolved organic carbon. And particulate organic carbon actually degrades faster than the annual input almost, based on the decay constant. So there's a lot of processing still happening there, but at the same time there's also substantial burial on the shelf. And then, of course, before the coastal release, there is a massive land area where all the river watersheds are located. And here a lot of things are happening too, and I'd like to say a few more words about this based on this so-called active pipe model that was published in 2007. So the fluxes I just presented to you, I call the lateral transport, or like the river mouth transport. They are about 50 teragrams. But people have also, of course, tried to put numbers on how much is actually emitted in the watershed, all the watersheds of these rivers. And these estimates are, not that well constrained, but better than the burial anyway. So a few estimates, for example, the whole boreal and Arctic regions emits about 640 teragrams CO2 as CO2, methane is not included here, from inland waters. A slightly more narrow focus here, purely the Arctic region and only rivers and lakes, had an elevation of 40 to 84 teragrams. So I tried to look at how big is this emission flux compared to the lateral flux, so the lateral carbon transport flux, the one which is the arrow out. And globally, people say this is, there's more emission than is laterally exported. But if you look at a couple of studies that actually quantify both fluxes, so both the lateral transport and the emission, it varies a lot. At some locations, the emission is much larger than the lateral transport, and at other places, it's actually much smaller. So it's not very surprising, but there are very large regional and system differences. So the burial flux is, as I said, the least constrained flux. Sometimes it's just basically closing the equation, and that's how they calculate the burial. And globally, it's said that there's less burial than there's actually laterally transported. And there are fewer studies that actually look at this. I don't think these are by far not all the studies, but this was a fairly quick search, and it showed that there was actually less burial than laterally transported. But other studies show that lakes in the Arctic are very abundant, and lakes, relatively speaking, store a lot of carbon. So I think the flux in the Arctic and the boreal region might actually be relatively large. Also because a study in 2009 showed that the Canadian boreal forest region alone stores already more than 10% of all the lake burial globally. So I think everybody's familiar with this Hugues' favorite field site. So I'm going to say a few more words about what actually determines the organic carbon release from thawing permafrost. And I think there are probably four main factors to consider. Permafrost type, the amount of ground ice, the topography, and soil type. So here you see a schematic of continuous and discontinuous permafrost. And if you focus on the blue arrows, you see that the hydrological flow paths in continuous permafrost are actually mostly constrained to the top layers, so the active layer and maybe some soil and vegetation overland flow. While in a discontinuous permafrost region, you have deeper flow paths because more of the ground can be accessed. So there's also more interaction with the soil in discontinuous permafrost regions. So longer flow paths, they affect this soil-water interaction exchange, but also the relative input of groundwater and the processing of material. So this will determine as one factor how much organic carbon you actually can release into aquatic systems after permafrost is thawing. Another important point in determining how much carbon you can see in a river or a stream after permafrost thaw is the ground ice content. So if you have permafrost with very little ice in it, there's typically thawing that occurs from the top down, and you have more leaching of soil organic matter into your aquatic system. And with more abrupt thaw, with permafrost with a lot of ice in it, this is a relatively quick process. Within a short amount of time, you get a lot of organic carbon being released. So the amount of, the type of thaw determines the amount, but at the same time, most likely, you have to look at more than just the release. The fate is also important. So with abrupt thaw, you get a lot of organic carbon release, relatively speaking, but most likely, lots of it just ends up in the sediments. So the soil type is a third point that is very important. Here you see an example of a study in the Yukon River in Alaska, where they measured the DOC load from July through to October in both the late 70s in blue on the top line, and then in red in the lower line in the early 2000s. And what they observed during this time, when permafrost in the catchment was slowly thawing, the DOC load was actually decreasing. A similar study, but then in a neighboring river, the Mackenzie, to the east, showed an opposite pattern. So at the same time, also here, the watershed experienced some permafrost thaw, but they observed the concentrations of DOC to be slowly increasing throughout the year. And then, of course, there are many differences between these two watersheds, but the main difference that is causing this, most likely, is that the thaw in the Yukon Basin has accessed more deeper soils that are mineral, so they absorb some of the DOC before it can be released into the aquatic system. While in the Mackenzie River, the increased thaw has exposed more organic soils, and that will lead to an increase in organic carbon. So it can be, yeah, you should know the soil type that is increasingly available upon thaw before you can say something about this. Of course, topography is also a very obvious factor. Here you see a slump in Selawik River in Alaska where, well, if thaw occurs on a gradient, it can continue to slide down and continue to expose new soils to thaw, whereas systems that are more flat, they could also thaw, but since there's no continuous removal of the material, it will result in a more stagnant situation. So after this release into the aquatic world, what happens with the organic carbon? Well, it can be degraded. And what determines this? There are also maybe even more factors important here, but I'd like to say a few more words about 4 of those. So the seasonality of rivers is important, but also the type of organic matter, the amount of nutrients that are available, and the residence time of the water, or actually the residence time of the organic carbon, both of it. Here again, an example of the Yukon River. There's lots of information here, in here, but focus on the bar diagrams, bar lines. They show the percentage of biolabile DOC. So it's basically an incubation after you filter the water, and they measure how much of the dissolved organic carbon disappears. So in percentage. And you can see that they've done this in 2 years for different times in the year. And the BDUC values are higher in the winter. So when there's base flow, so not during the summer and the spring, there's apparently more labile DOC in your river. But at the same time, on the north north slope of Alaska, a study by Max Holmes showed that basically a little bit of the opposite pattern. So spring freshet material, which is the first peak after ice out, with lots of material in May and June being released. These tundra rivers, smaller rivers, they showed the highest lability during the spring freshet. And this is also most likely related to the type of organic matter that is coming out. So that brings me to the next point. Here, organic matter, the composition of organic matter is important also to determine how labile it can actually be in the environment when it's released. So this is an example of a study where different thermokarst waters in Alaska have been sampled. And again here, the DOC lability has been assessed, but at different locations. And these locations represent different activity levels of collapsing permafrost. So on the left, you see reference data points of stable situations that are not slumping. And then to the right, you see during the peak of the slump and where there's lots of active degradation, and it's slowly getting more stable and vegetated again, for example. And you see that the highest DOC losses are at the moment when there's, the slumps are most active and there's most fresh permafrost being released into your systems. So that organic matter at that moment is also most directly from permafrost. So here another example of the organic matter composition. This is a rather fancy technique, FTICR-MS, mass spectrometry technique that results, I think you can see it best here, in these so-called Van Graevelen diagrams, where every point basically represents part of your molecular composition. So here they did incubations with thaw streams from Yedoma exposures. And you can see here, after 28 days, all the red points basically, they represent an increase in these parts of the molecular structure. And all the blue points represent a decrease. So you can derive the unique molecular formula of these thaw streams by looking at this technique, because all the blue dots that are very aliphatic, high in hydrogen-carbon ratios, they are disappearing during incubations, and they are very typical for Yedoma permafrost. Nutrient availability is also very important. These are two examples of two different river systems where you see that more inorganic nitrogen, or in other words, lower DOC total nitrogen ratios, result into higher DOC losses. And aquatic residence time is also something that plays a large role. This is an example of northern Sweden, the Stordal and Meyer catchment. I don't think you can read the numbers, but anyway, in green are the lakes. They have relatively low aquatic carbon emissions, whereas some of the streams are dark red, and they have very high carbon emissions. So the streams receive organic matter from the soil very directly, and so this material is fresher and can be degraded instantly, while in lakes, the organic matter has been floating around for a while already. Similar pattern is seen here, where from left to right, you see the Kolyma main stem, where not a lot of organic matter is being degraded, but if you move up in its watershed towards smaller streams, you see that there's actually much more being degraded. And this is nicely summarized in this graph, showing kind of like the different arms of a river watershed. And in darker red, it's the fresher permafrost material that is rapidly degraded before it actually arrives in the main stem. So lots of the material that accesses a stream will never actually make it to the river mouth because it's degraded along the way. So finally, what can we say about the future? Well, this remains, of course, always a predictive set of statements. But this is one approach one follows, which you briefly saw also in the video at the beginning of this session, where a lot of Arctic hydrological experts have been asked for their opinion about how they thought aquatic fluxes are going to change in the future. And they were asked to classify this into dissolved organic carbon, DOC, particulate organic carbon, POC, and coastal erosion for 2 different time points in the future. I think there were actually 3, but for visual purposes, I removed one, and then for 4 different temperature scenarios. And there was quite some consensus on an increase in organic carbon export to the ocean in the future. With a side note that for DOC, people thought they had most knowledge, and there also was least consensus. So 20% of the people that were asked about dissolved organic carbon releases in the future were hesitant. They thought it would stay neutral or actually decrease, and they attributed this to, for example, deeper, longer flow paths or higher biolability or photolability and higher degradation. So I'd like to summarize with a few things that I kind of collected from this talk and where we could maybe, well, hopefully do something with. I think dividing it again in like active layer deepening as a thaw type, abrupt thaw, and coastal erosion. I think we basically all agree that most of these features are increasing. So there's increasing thaw and increasing coastal erosion. So what determines then the organic carbon release going into the water? That of course depends on the features of this newly thawing layer of soil. And the properties, how much ice, how much organic carbon, how much nutrients. That's one feature. And then also, to determine the aquatic release, you need to know how accessible the water is. And on both thaw types on the right, so both with coastal erosion and abrupt thaw, you have much more direct release into your aquatic system. Whereas active layer deepening might never see the light of water, as you can say it, because it might never reach a stream or a river, or it's actually very close to a stream or river. So the connectivity is important to determine the release. So I'd say organic carbon release is more variable with that type of thaw, and probably with the abrupt and coastal erosion part of the story, we get more likely an increase in organic carbon release. Yeah, so thank you, and